essentially to write down LoRa expansion, I said I would first like to get an analog of Cauchy integral formula. So this was the formula, and which I wanted to establish. And for that, what did we see? We took the exactly the same function like in the proof of Cauchy integral formula. The same function g we took, and then we observed that the integral of g along this circle of radius r1 or the circle of radius r2 centered at a, both the integrals are the same. Okay, so that is not very difficult to prove. I have kind of told you the idea how it is done. And once I have this two equalities, so I can substitute the value of g over there, and I get an equality of this kind, and which can be further written in this form. So I need to show f alpha in terms of some integral, and I have written my f alpha in this form. So far I have this one. Now I really need to take care of this 1 upon z alpha part. So what did I do? So for the first integral, here my z lies on the circle of radius r1, and remember my alpha is, or this r1 r2 are so chosen that mod of alpha minus a is less than r1, but it's bigger than r2. Okay, so accordingly, depending on which integral I am taking, I have to do the adjustments. So fine, here I wrote 1 by z minus alpha, so this one was 1 by z minus a minus alpha minus a. So I take z minus a out, and I get 1 by 1 minus alpha minus a divided by z minus a. And on r1, clearly this has absolute value less than 1. Like on a plus gamma r1, this has absolute value less than 1. So therefore, I could expand it as an infinite series. And as I said, this converges for mod of alpha minus a divided by z minus a less than 1. And this is precisely what happens in this circle a plus gamma r1. Now, if I go to a plus gamma r2, there what we know is that mod of z minus a is r2, which is less than alpha minus a. So therefore, there while expanding 1 by z minus alpha, I have to be slightly careful. So I wrote it as a minus alpha minus a minus z, and a minus alpha if I take out. So this is 1 minus a minus z divided by a minus alpha, which I could write minus 1 over alpha minus a 1 upon 1 minus z minus a alpha minus a. Now if I expand it like this, then I can write this one in an expansion, and I get that my 1 upon z minus alpha is minus of n bigger than or equal to 0 z minus a power n alpha minus a power n plus 1. Okay, so this is precisely what I am getting. Fine. Okay, now that I get this, observe here, this is my integral. Okay, so here let us be slightly careful, and let's try to do this integration. So integral a plus gamma r2 1 upon z minus alpha, this integral, of course this convergence is uniform. This convergence that I have written, this convergence is uniform on, for example, a plus gamma r2. Okay, so do you agree to that? That the convergence, like I wrote 1 over z minus alpha in this form, that formulation, like the convergence of this infinite series is uniform, right? Because here mod of z minus a divided by alpha minus a is strictly less than 1. So if that's the case, then I can write this as summation n bigger than or equal to 0 with a minus before, and then a plus gamma r2 z minus a power n divided by alpha minus a power n plus 1. But alpha is just alpha and a, they are just constants. So this is n bigger than or equal to 0, 1 over alpha minus a power n plus 1, integral over a plus gamma r2 z minus a power n. Okay, so this guy, you can now tell me what is this integral? What do you think? integral a plus gamma r2 z minus a
Zero.
power n. This integral is 0 because this is just same
N
integral.
is greater than equal to 1.
N is greater than equal to 0 even, right? So this is same integral as integral over gamma r2, just z power n, doesn't matter. So you can also substitute the formula and you will see that this integral is 0. So therefore this quantity is 0. That's good. So therefore what happens? This integral goes away, right? That becomes 0. Fine, let us now focus on the other one. So now I have to integrate. So integral a plus gamma r1 1 upon z minus alpha. Okay, so that's the this component I'm now looking at. So what do I know there? There I know that the function actually looks like this. So fine, we will substitute it there. So there the function is a plus gamma r1 1 over z minus alpha looks like n bigger than or equal to 0 a minus alpha power n z minus alpha power n plus 1. And again there the convergence is uniform, so I can write n bigger than or equal to 0. A minus alpha power n really does not matter, this is a constant. Integral a plus gamma r1, and now I have 1 upon z minus alpha power n plus 1. So now tell me what is these integrals? What can I say about them? Yeah? Tell me what do I get over here?
2 pi I.
Coming from which term, Abhishek?
N equals to 0.
And what happens to n other n's?
0.
Very good. So this is 2 pi I. Okay. 2 pi I, of course, n equal to 0 means there is no a and a minus alpha. So only for n equal to 0 term, this integral is going to survive, which is going to give you 2 pi I. And for all other things, this integral is going to be 0. Primarily because you know already this has primitive and all this. So this integral is 2 pi I. So therefore, what do I get? This integral already was 0 and this integral came out to be 2 pi I. So therefore, what I get, hence we get f of alpha is equal to 1 over 2 pi I, exactly what I said, f of z divided by z minus alpha minus f of z divided by z minus alpha. First integral is over a plus gamma r1, second integral is over a plus gamma r2. Okay, so this is the formula which I had. Fine, so let us write it down. A plus gamma r1 f of z divided by z minus alpha minus 1 over 2 pi I a plus gamma r2 f of z divided by z minus alpha. Okay, so is it clear this Cauchy integral formula, the analog of Cauchy integral formula in this case? Yeah, clear to all
Yes,
of you?
sir.
Fine. Okay, so whatever analysis that we did so far, there the involved factors were, as you can see here, I was expanding z minus alpha. Here also I or 1 over z minus alpha. Here also I expanded 1 over z minus alpha. So why don't we use those expansions over here? Okay. So if I do like use these expansions over there, what I am going to get, yeah, on these circles. So if I use those expansions, I am going to get this is 1 over 2 pi I integral a from gamma a plus gamma r1 f of z into summation n bigger than or equal to 0 a minus alpha power n divided by z minus alpha power n plus 1 minus 1 over 2 pi I integral a plus gamma r2 f of z times here n bigger than or equal to 0. Here it is the other way around. Z minus, sorry, this is z minus a, right? A minus alpha, sorry, z minus alpha, that's fine. Yeah, and here, what do I have? I have in this case, just now I did z minus a alpha minus, just a moment. What did I write? Yeah, so this is alpha minus a, z minus a. I made a mistake. This is alpha minus a, z minus a. Sorry, so here it is z minus a Here also I wrote something wrong. Alpha minus A, Z minus E. Yeah. Okay. Now this is Z minus A. I hope in the previous one I wrote correctly. Yeah. Okay. So here I have Z minus A power n and then alpha minus A power n plus 1. Okay. So this is what I get, and overall you see again I have uniform convergence of all these infinite sums. So they can be written, maybe I'll write it in this page itself. So this whole thing can be written as summation. I can take out the summation n bigger than or equal to 0. I can write Cn. I will tell you what is Cn is. Cn alpha minus A power n minus, or I can write it as plus, summation. Note here that this n is bigger than or equal to 0, and here alpha minus a has exponent n plus 1. Okay, so in the denominator I get starting from alpha minus a, then alpha minus a square, alpha minus a cube, and so on and so forth in the denominator. Okay, so I can write this as n less than 0 dn alpha minus a power n. Okay, I just need to be careful how do I write cn and dn. Where, so what's my cn? My cn is where for n bigger than equal to 0, cn is just nothing 1 over 2 pi I. This is exactly like the power series expansion. So exactly whatever we had, this generalized Cauchy integral formula, exactly that one. This is what is Cn, and in case of Dn I just have to be slightly careful. For n less than 0, what is Dn? Dn is that we can see this is fz into z power n over here, and that's corresponding to n minus 1. So therefore this Dn is going to be 1 over 2 pi I a plus gamma r2 fz divided by z minus a power n plus 1 again. Okay, but here remember this is n negative. Okay, so if n is negative, then of course this one is n plus 1, that one is less than or equal to minus 1, and or rather less than, yeah, n plus 1 is going to be, yeah, this is fine, n is negative, so n plus 1 is strictly less than, uh, yeah, this is less than 1, so therefore minus of that will be bigger than or equal to 1. So therefore exactly what you are getting over here in the exponent, we are going to have that only. Okay, so therefore this is what we get if I put everything together, that I am going to get a LoRa expansion around a in terms of alpha, where the coefficients are given in this form. And this is precisely if we go back, I don't know if it is in this, yeah, if we go back, these were the formula for powers, the coefficients. Where did I write? Somewhere, yeah, you see this was the expression exactly in case of formal LoRa series, where of course the center was at 0, am was 1 over 2 pi I gamma r fz by z power m plus 1. Exactly this is what we have, and this is exactly what we take over here. Okay, this is what precisely we get. Of course here you need to be slightly careful, because here there is a minus which is involved. So just let me see, did I take care of the minus properly? Just a second. Yeah, so when I substitute, this minus becomes plus, because yeah, that is what we have, right? I had a minus over here, and when I substituted in the expansion, here already there is a minus, so minus minus becomes plus, so I get this. Fine, so this is precisely what we are getting as a LoRa expansion. Okay, so now this shows that any function which is holomorphic in an annulus will be having a LoRa expansion. Okay, so what did the theorem say? It said that no matter what holomorphic function we take in an annulus, it's going to always have a LoRa expansion. Okay, so therefore, as a corollary, what I can say is that let alpha be an isolated singularity. So if I have an isolated singularity of f, then f has a LoRa expansion summation n in z, a n z minus a power z minus alpha power n uh, on a deleted neighborhood b alpha r minus alpha. Okay, for some r positive. Okay, because if I have an isolated singularity, then by definition I have a deleted neighborhood where the function is holomorphic, and once the function is holomorphic in a deleted neighborhood, we know deleted neighborhood can be treated as an annulus. I have told you already, rho 2 is equal to 0 and rho 1 is equal to r, let's say. Then in that deleted neighborhood, I will get a LoRa expansion. Okay, so in general, we have seen that holomorphic function on annulus, they have LoRa expansion. So if I take any isolated singularity of a function, so then we know that the function is going to be holomorphic in a neighborhood around that point, except for that point. So in that neighborhood, we can write down a LoRa expansion. Okay, so here I need some definitions so that we can associate things rather easily. Okay, so let summation n over z a n z minus alpha power n be the LoRa expansion of be the LoRa expansion of f around alpha. Then I have two things. Then the series summation n less than 0 a n z minus alpha power n. So I have this part with negative exponents. So then this part is called the principal part, called the principal part, principal part of f. Okay, so why principal part? Because this is the part which is going to determine the type of singularity that alpha has. Okay, so that's the main part, so that's why this is called the principal part. And the n bigger than 0 or bigger than equal to 0 a n z minus alpha power n is called the holomorphic part. Okay, so holomorphic part is the one which is coming from the power series. That's natural, that's going to be holomorphic at that point. And the principal part is which effectively determines what is the type of singularity that we have and all of this. Okay, so therefore that's the main part. as far as the singularity is concerned, and this is why it's called the principal part. Okay, so now the point that I would like to mention, which I have told in the last class also orally, is that let me write it in different ink. The principal part, the principal part determines the type of singularity. At alpha. Okay, I have of course told you already orally that, for example, if I have a removable singularity, then that means actually that's not a singularity. uh, just by making a change of the value assigned at alpha, we can make our function to be holomorphic. So therefore, now once my function is holomorphic in the whole ball, we know that the function will have a power series expansion, and now we also say that there is a Laura expansion. Okay, so therefore it will turn out that the principal part in case of removable singularity will be identically zero. And if you think of polar singularity, then we will see that the principal part is going to be finite. And in case of essential singularity, like exactly what we saw in case of exponential 1 over z, we will have infinitely many terms in the principal part. Okay, so that infinitely many terms, they are going to dictate the behavior, or like make the behavior so random. Okay, so that's the main reason why the like that why around an essential singularity the function behaves so erratically, is because of this principal part, because there are so many terms, infinitely many of them. So it's really like depending on the, for example, sign of the coefficients, or depending on the coefficients themselves, the value could be completely, the values can be very different, like depending on them. So you cannot really predict the behavior of the principal part. That's the main reason. Okay. Why it uh, why we see phenomena like what has been mentioned in Casarotti-Vestas theorem. Okay, so what's the theorem regarding this? Let me now write it down. I have already told you this so many times now. Alpha is a removable singularity if and only if the principal part. Yes, somebody was saying something. Okay, so this is the statement. Okay, now of course, if the principal part itself is zero, that means you are saying that your Laura expansion itself starts with a holomorph. It's given by a power series, and we know that power series are holomorphic functions that becomes holomorphic in the center also, of course. So therefore, alpha becomes removable. Okay, so proof: principal part is zero. That implies Laura expansion around alpha is actually a power series expansion. So you can just take that power series to be the function g. Okay, so alpha is removable. Okay, as power series defines holomorphic function on open domain of convergence. Okay, so in particular in the center aspect. Okay, that's fine. Now, if I have a removable singularity, I need to show that my Laura expansion must be having no principal part. Okay, so next let alpha is alpha be removable. Okay, so I'm assuming alpha is removable. So there exists some function g such that g is holomorphic in B alpha r such that your gz is equal to f of z for all z in B alpha r minus alpha. So this is what I am given, and I have to show that the principal part of f is not there. Okay. Now let's write down the Lorentz expansion of f, and then we will see how we can show that. Fine. So note that on B alpha r minus alpha, my f of z is of the form n over z a n z minus alpha power n. Okay, and if you remember, what was my you know what was my an? An was of course 1 upon 2 pi I, let's say alpha plus gamma t f of z divided by z minus alpha power n plus 1. Okay, so here what I'm going to take, my t is somewhere in between 0 to r. Okay. So like here what we had initially, you see I wrote dn and cn in this form. Of course here I wrote a plus gamma r2 a plus gamma r1. Essentially the point was that the circles that I am taking, they should be somewhere within the domain of holomorphy. Okay, so those my circles were in that region. So now that I have a punctured disk, I'm just taking both r1 and r2 going to be the same. Anyway, that's not going to make much of a difference. Okay, so anyway, I take an is like this, and now what we can see is that this is what is my an. Okay, so this is for all n in z. Okay, that's what I have. Now let's take n to be negative. I need to show an is 0. So take n negative. So in that case, I need to show an is equal to 0. Now what is an? An is 1 over 2 pi I integral alpha plus gamma t f of z divided by z minus alpha power n plus 1. Now I know, so of course in on this circle, my f is same as g. So I can write this is g of z into z minus alpha power, let's say minus n minus 1. Okay, so this is precisely what I have. Now note here n is negative. So this implies minus n is bigger than or equal to, or like n is less than or equal to minus 1. So therefore minus n is bigger than or equal to 1. So that implies minus n minus 1 is bigger than or equal to 0. Right? So this is what I can. Okay, so this implies this, this implies this, this implies this. So what I get is that minus n minus 1 is non-negative. So therefore, what do I see? This is actually a holomorphic function. Okay, and g was anyway holomorphic. Okay, so this part is a holomorphic function, g is a holomorphic function, and like these are all holomorphic functions on bar. Okay, so note gz into z minus alpha power minus n minus 1 is a holomorphic function on B alpha r. On this whole ball, this function is holomorphic. So what can I say about holomorphic function, integral of a holomorphic function along a closed curve?
0.
0.
I
So,
close curve.
yeah, so an is equal to 0 for n negative. Okay, I cannot say the same thing for n positive. Remember that, because if n is positive, then here whatever 1 upon z minus alpha that I am having, or if n is non-negative, then that is not holomorphic anymore, right? So then I will not be able to say that. Okay, so we have to be careful there. And here, of course, I am getting this. Both the things are holomorphic, and therefore I get this. So all my ans are 0 for n less than 0, and therefore what we get is that the LoRa expansion is essentially only a power series expansion. Okay, so that's the first statement, which is about the removable singularity. And exactly like before, we are going to next write down a statement which will be about the what do you call the polar singularities. Okay, so let us see. Let alpha be a polar singularity of f of order m. Okay, so this is what we have. Okay, uh, then I can say that then in the LoRa expansion of f around alpha, we have a minus m is not equal to 0, and a n is equal to 0 for all n less than minus m. Okay, so this is what we are going to have, and in fact we will also say when the converse is true. So the converse being true is very easy. Okay, because converse being true means I am just going to take a LoRa expansion which starts with a minus m, and I'll just take out z minus alpha power m. That's going to just be a power series. Okay, so therefore the converse part is anyway triviality. We just mainly focus on the first part. So if alpha is a polar singularity of order n, then I am saying that the LoRa expansion around alpha has only, not only I'm seeing only finitely many negative exponent, but I am telling you that if m is the order of the pole, then after m no other negative exponents are going to appear, and also the mth coefficient, or a minus m, that means z minus alpha power n, that coefficient is going to be non-zero. Okay, so this is what I can say about LoRa expansion and a polar singularity. Okay, so this is exactly what we have. So m here is of course bigger than or equal to 1. You can take, let's say. Okay, fine. So how do I prove this? So since f has a pole of order m at alpha, what did we see? We actually had seen that we can write f as f of z equal to some gz divided by z minus alpha power m in a neighborhood, or rather in a deleted neighborhood, in, let's say, b alpha r minus alpha for some r positive. Okay, so this is what I have. This is what we can write. We have seen this already, right? This is how, and of course here I should write, we can write where G is holomorphic on B alpha R. Okay, so this is how it looks like, and G of alpha is non-zero. Okay, so this is how it looks like. This is coming from the definition of pole, and of course the analysis that we have done before about polar singularities. Fine, so once I have this here, from here what can I notice? Note that if I consider this function z minus alpha power m times f of z, then note that this has Like, so what can I say? Z minus alpha power m times f of z. This is equal to g of z on the deleted neighborhood, and g is holomorphic on b alpha r. So from that, what can I say? I can say that z minus alpha power m times f of z, which is anyway holomorphic on b alpha r minus alpha. So this function, therefore, at alpha there could be a singularity, but the singularity is what kind of singularity?
Removable.
Very good. Has a
Removable.
yeah, removable singularity at alpha. Okay, very nice. Now let's write down the expansion. So suppose I know that f will have a lot of expansion. So suppose f of z is n in z a n z minus alpha power n. Suppose I have this. So what do I get? So if I just imagine z minus alpha power m. M is positive, you should keep it in mind. F of z is equal to n in z a n z minus alpha power n plus m. Right? This is what I can get. I just multiply and I get this. So what can I say now? Look at this expression and tell me what do I get? Which coefficients do I get 0 from the fact that alpha is a removable singularity? From alpha being a removable singularity, we get which coefficients to be equal to 0? Tell me. For which n plus m is less than 0, right? Isn't it? So we get an is equal to 0 for all n plus m negative. That is n less than minus m. Agreed, all of you? This is because this guy has a removable singularity, and about removable singularity, we just proved the theorem. Correct?
Yes, sir.
Now, what else can I say? I know that, for instance, g of alpha is not equal to 0. Now, if g of alpha is not equal to 0, so that means, of course, when this has, you know, a removable singularity, so at the point alpha, I should also get that this function does not vanish, right? So if you look at this power series, how do I get the value at alpha? Of course, I know that all the negative exponents are not there, so it's only positive exponents. So z minus alpha power m into f of z is n bigger than or equal to minus m a n z minus alpha power n plus m. Now here, tell me, therefore, how do I get the value for this function? What is the value at alpha? The function at right hand side. What is
And
a minus m, right? So uh, RHS takes the value a minus m at alpha, which is supposed to be, of course, same as g alpha, because of course right hand side, this is a polynomial, this is a power series, so this is a holomorphic function, and this matches with z minus alpha power m into f of z, which matches with g, and g is a holomorphic function. So by identity theorem, this power series and g, they are the same function. Okay, which is nothing but g at alpha. We know g alpha is not equal to 0, so a minus m is not equal to 0. So that's it. That's the statement which we have mentioned. We get that this quantity is not equal to 0. Okay. So what did I say? Here z minus alpha power n times f of z is written in terms of a power series. That power series, of course, defines a holomorphic function. G is a holomorphic function. Both of them are equal to z minus alpha power m into f of z on a deleted neighborhood, and by identity theorem they must be equal on the whole in the whole neighborhood. And if you just evaluate at alpha from the power series, you are getting the value to be a minus m, and we know g alpha is not equal to 0, so therefore g alpha a minus m must be not equal to 0, because a minus m is nothing but g alpha. Okay, so this is how the Lorentz expansion around the pole looks like. Okay, so it only has finitely many terms in the principal part. Whatever is the order of the pole, that coefficient is going to survive. That's not going coefficient is not going to die. Okay, it's going to stay there. Okay, so that's fine. And
Hello,
now,
sir.
no?
Hello, sir.
Yeah.
Sir, z minus alpha to the power m fz equal to gz, and gz is holomorphic on b alpha r. So, how can we say that alpha is removable singularity for a gz?
G is anyway holomorphic. I said alpha is a removable singularity for this function.
But it's equal to gz, na?
Yeah, so it's equal to gz where? It's equal to gz on this set, right? Correct?
Okay, okay.
Is the definition of removable singularity. You need that there must be a holomorphic function around that in a neighborhood around that point where the function such that that holomorphic function is equal to your original function in the deleted neighborhood. Like if you remove the point alpha, then you have equality, but the holomorphicity of G should be there in the entire disk, right? That is what is the definition of a
Yes,
removable
sir.
singularity, right? So this is what exactly we get. Fine. Is this clear now?
Yes, sir.
Okay, great. So therefore, we are done with this one. And I said, of course, the converse is very easy. So if I write f of z is equal to summation n bigger than or equal to minus m a n z minus alpha power n, then I am just going to take gz equal to f of z into z minus alpha power m. So if I take this, then gz becomes n bigger than or equal to minus m, at least in a deleted neighborhood, a n z minus alpha power n plus m. Okay, so then, and this guy is holomorphic, of course, holomorphic on b alpha r, because this is given by a power series which is convergent. And in fact this has same radius of convergence, like you guys have seen already, n bigger than or equal to 0 a n x power n, and let's say n bigger than or equal to minus m uh, a n x power n plus m. They have the same radius of convergence. It doesn't matter really. Few terms, like changing, if you just shift your coefficients by something, right? Here it's only matter of changing some few coefficients. So changing few coefficients or adding some few extra coefficients in the beginning, they do not change at all the radius of convergence. Okay.
Sir, sir, your voice is breaking.
Yeah, what I'm saying is that you guys already know that a n x power n, for example, if I have a n x power n, and then if I just say that, okay, just before a n, you add few more terms in the sense, let's say for coefficient of
Sir,
constant.
your voice is not clear.
Hello, am I audible? Is it better? Yeah.
Yes, sir.
Yes,
Sir,
sir.
yes.
Clear.
Yeah, so what I am saying is that this a n x power n, whatever is the coefficient of this power series, if you just give a shift in the sense, the same coefficients are going to appear, but let's say somewhere little bit later. Okay, so initial few coefficients, let us change. Let us give some new coefficients in the beginning, and whatever like a naught, a1, all those things are going to appear, but let's say after some time. Then if you do that, there is not going to be any change. Okay, as far as the uh, radius of convergence is concerned. Of course, if you think in terms of the formula of radius of convergence by ratio test, given all your ans are non-zero, then that is in fact trivial, because eventually all the ratios are going to be the same, right? But like the ratios which are going to matter. But if you want to take the nth root, you can also do it in that way. Okay, so there is not much difference. So this guy is also going to be a holomorphic function. It does not really matter if you change few terms, and you have f of z is equal to g of z divided by z minus alpha power n. Okay, so therefore alpha is a polar singularity of order m. Of course, g of alpha is not equal to 0 because it is given a minus m is not equal to 0. So Therefore, g of alpha is of course not equal to 0. So this converse part is actually a triviality, as I said. So there is nothing in that converse thing. Okay, so anyway, this we get, and therefore, like I said, I was telling you to all the time keep the example of exponential 1 over z in mind. We get as a corollary. I'm not going to do it more explicitly, it's already done. Alpha is an essential singularity of f if and only if the Laura expansion of f around alpha has infinitely many, like infinitely many an not equal to 0 for n less than 0. Okay, so infinitely many n should be negative non-zero for n negative. Okay, so n is not equal to 0 for infinitely many n less than 0. Okay, so I hope this is clear, this corollary. Yeah, because essential means it's neither removable nor polar. Okay, so it cannot, it must have, like if there is no principal part, then it will be removable, and if the principal part is finite, we know it's going to be polar. So therefore your principal part has to be infinite, and that means the negative coefficients ans are going to be non-zero for infinitely many ans, right? Okay, clear this one? Yes or no?
Yes, sir.
Okay, fine. So now, of course, we have done, means once we are done with this LoRa expansion, what we are going to do next is that we are going to learn integrating functions. Of course, we have seen integration of holomorphic functions on a path and all that. We have seen how to even, means of course, we know integrating holomorphic functions. This time what I am going to do, I will be interested in taking integration, like, or doing integration of functions which are having some kind of singularity. Okay, so while doing this, you need the example that I will ask you to keep it in mind is the example of 1 over z. Okay, so if you remember, we had done that integral of 1 over z in the on the circle e to the power I theta for theta between 0 to 2 pi, that integral was 2 pi I, right? Whereas if we take integral of 1 upon z square, then that integral was equal to 0. Okay, so let me just now write integration of functions with singularity. Okay, so the main focus will be polar singularity here, as we shall see. Okay, because somehow we want to use the LoRa expansion and talk about the integral and all this. Okay, so here, like I said, the thing that you need to remember really to understand this theory well, or like let's say when we encounter this Cauchy residue theorem, it will be very clear why really Cauchy residue theorem is there. Okay, so here what you need to keep it in mind is that this integral 1 upon 1 over z, let's say e power I theta, or theta between 0 less than or equal to theta less than or equal to 2 pi. This integral was 2 pi I, right? And the same integral over e power I theta 0 less than or equal to theta less than or equal to 2 pi 1 upon z square was equal to 0, right? Okay, now notice here both 1 upon z and 1 upon z square, both of them have polar singularity at z equal to 0, right? Isn't it? Both of them have polar singularity at z equal to 0, correct? But whereas the behavior of 1 upon z is slightly different from the behavior at 1 upon z square. Okay. Of course, you can say that, sir, we have seen already that 1 upon z does not have a primitive on the circle, whereas 1 upon z square actually has a primitive on the circle. Yeah, so that's one difference, of course. But we would also like to see a difference from the point of view of the LoRa expansion. Okay, so there will be one particular coefficient which is going to be very important in this particular study, which is the coefficient of 1 upon z minus alpha. Like, let's say if alpha is a singularity, then we will be able to write down the LoRa expansion. The coefficient which is going to play the most important role is going to be the, in case in the integration theory, is going to be the coefficient a minus 1. Okay, so in case of 1 upon z, just it's already in the expression of a LoRa expansion. I see that the coefficient of 1 upon z there, it is equal to 1, which is a non-zero coefficient. And in case of 1 upon z square, which is also in the expression of a LoRa expansion, there the coefficient of 1 upon z is actually 0, right? So there that particular a minus 1 for 1 upon z square is actually 0, around 0 when we write down the LoRa expansion. So this particular coefficient a minus 1, as I said, that's going to play a key role. And this is what we are going to see, that whatever the integrals that we have done in special cases, we can see that we will be able to sum them all of up, and we can present one formula which is going to, take care of all these special integrals that we have done, of course, for uh, integrals over closed curves. Okay, I have seen while checking minor copies, some of you have blindly used certain results which were only for closed curves, for event curves which were not closed. Okay, so please be careful here. We will be talking about, you will see this Cauchy-Decidue theorem, which will be integral along a closed curve for functions which are going to have some kind of singularities inside that curve, and we will see what the integral is going to come out to. Okay, so let's see why. As I said, I have already explained this term, the coefficient a minus 1. So let us see why it is really important, and from the point of view of integration theory. Okay, so alpha, let's say an isolated singularity of f, and f, let's say, is holomorphic on b alpha r minus alpha. Okay, so let's say I have this, and now if, let's say, I have 0 less than capital R less than little r, uh, then what is, my question is, what is integral of f over, let's say, alpha plus gamma capital R. Okay, so I want to understand what is this integral. Okay, now I know I can write down an absolutely convergent or uniformly convergent LoRa expansion. So we can write f of z is equal to summation n over z. So this is uniformly convergent on any compact subset, this LoRa expansion, a n z minus alpha power n on b alpha r minus alpha. So this is what it looks like, and this converges uniformly on all compact subsets. Okay, because you can show normal convergence on any compact subset. So subset of b alpha r minus alpha. So on this deleted neighborhood, I have uniform convergence. Okay, and since I have uniform convergence, when I think of this integral f alpha plus gamma r, this integral is nothing but like exactly what we have been doing, n over z a n integral alpha plus gamma r z minus alpha power n. And you already know this is the same integral as z power n integral over gamma r, and this integral is nothing but 2 pi I if n is equal to -1 and 0 otherwise, right? So this is 2 pi I into a minus 1. Okay, so therefore, this integral, yeah, anyway, so this is what the integral is coming out to be. Okay, so is this clear? Yes.
Yes, sir.
So from the integration, from the aspect of integration theory, what we see is that this a minus 1 plays an important role. Important role. Okay, this is what it is, and so let us give a special name to this a minus m. Okay, so the coefficient a minus 1 is called the residue of f at alpha, and we denote it by residue f at alpha like this. Okay, so what is residue of a function at alpha? This, so you just write down Laura expansion of your function around that point in a deleted neighborhood, and then whatever is the coefficient of z minus alpha 1 upon z minus alpha, that is your residue. Okay, so that's a minus 1 is the residue of f at alpha, where a minus 1 is the coefficient of z minus alpha inverse in the power Laura expansion of f. So if, for example, your singularity is a removable singularity, or let's say your function is holomorphic around a point, then of course your residue is going to be 0. Okay, so there is nothing surprising that when we integrate holomorphic functions in a closed curve, okay, or piecewise smooth closed curve, there we get that the integral is equal to 0, because there my a minus 1 is actually 0, right? So 2I pi times a minus 1, it's going to be still 0, isn't it? Is it clear what I'm saying? So we have seen already that integration of f over a closed curve when f is a holomorphic function is going to be 0, but that comes automatically, isn't it? Yeah, now with that, with this understanding, it comes automatically. And also what we see is that the integral of 1 upon z square is naturally 0, because 1 upon z square does not have any residue, isn't it? Clear? Yeah, tell me if it is not clear, I'll repeat. Is it clear that in case of this integration theory, how the integral is going to give you the coefficient a minus 1, and therefore, of course, if you take any function whose a minus 1 is equal to 0, when you integrate, like means when you integrate along a path where inside except for alpha all other points I have all holomorphicity and all this, and then if you integrate there, all you are going to get is this a minus 1 up to a integral multiple of 2 pi I. So if your a minus 1 is equal to 0, so your integral is going to vanish. Clear?
Yes, sir.
So this one, as I said, is called, it's given a special name. It's called the residue. Okay, fine. So now what happens is that uh, it may so happen is that, like, once I am giving you a function, you might not be, you are, let's say, not able to find out the Laura expansion immediately. Okay, let's say you cannot do that, and then if it is not, you do not know the Laura expansion, how will you know the residue? Okay, so it turns out that in certain cases you can figure out the residue from other informations. Okay, so, or like the form of the function and all that. Using that you can figure out the residues. Okay, so let us do some residue calculation. Okay, so formula to find residue calculations. So as we see that to find out the integral, it's really important to understand the residue. So therefore let's do some residue calculation. Okay, so the first thing, like I have already mentioned, if alpha is a removable singularity, then if alpha is a removable singularity, then what is the residue? Tell me.
0.
This is equal to 0, of course. And now if alpha, somehow somebody tells you that alpha is going to be simple pole of f, okay, then how do we calculate the residue? Okay. The calculating residue is very simple in that case as well. Okay, so next case, case 2, alpha is a simple pole of f. So I want to figure out what is the residue at alpha. Okay, so here what we are going to do, you see, I need to know the coefficient of 1 upon z minus alpha of f around alpha. So I need that coefficient. So what do I do is that I have my f, which is having a simple pole at alpha. So it starts with, let's say, some a minus 1 divided by z minus alpha plus a naught plus a2 plus a1 z minus alpha plus a2 z minus alpha square, and so on and so forth. And I really need to know about this a1. Okay, so I have told you always that, for example, when you think of finding out coefficients of power series, what you should do, you should try to evaluate that power series at some point. Okay, so like for example, if I need the nth degree coefficient, you take derivative n many times and then you evaluate, and that point alpha you get the coefficient up to some multiple. So exactly the same thing which we are going to do for finding this residue as well. So what we are going to do, we are just going to multiply my function f by z minus alpha, and the new function therefore now becomes exactly like in the previous case, is now becomes means this new function now becomes a function having removable singularity and z minus alpha. So what you do, you just look at the limit as z tends to alpha, z minus alpha times f of z. That's going to give you in return your coefficient a minus 1. So therefore, calculating when your alpha is a simple pole, suppose you know, then that calculation also becomes quite simple. Okay, so if alpha is a simple pole, so let me write it down. Then residue of f at alpha is limit z tends to alpha, z minus alpha into f of z. Okay, so that's one form, and here I will also write another form. This is one, another useful form here. Suppose f of z is equal to az by bz in a deleted neighborhood, and a of alpha is not equal to 0, b has a simple 0 at alpha. So that means b of alpha is 0, but the derivative of b at alpha is not equal to 0. So this has a simple 0 at alpha. Then I can give you another formula. Residue of f at alpha is a alpha divided by b prime alpha. Okay, we will see how to get both of them. Okay, so the first one I have already told you, the first one is very easy. So write f of z is equal to a minus 1 z minus alpha plus a naught plus a1 z minus alpha plus so on and so forth. So let us write like this. So then this implies z minus alpha is a minus 1 plus summation n bigger than or equal to 0 a n z minus alpha power n plus 1. Okay, now this is what I get, and this equality is valid. Sorry, here z minus alpha into f of z minus alpha into f of z is equal to this. Okay, so this is what I get, and now for example here this equality is of course on b alpha r minus so this equality is true on b alpha minus alpha r minus alpha. Now I am supposed to calculate limit z tends to alpha z minus alpha f of z. But when we take limit at a point of a function, we generally do not need to bother about the functional value at that particular point, right? We can just look at the function around that point and we can determine the limit. So this limit is therefore by this equality. You can see here from this expression, of course this is a power series expression which has the same radius of convergence as this particular power series. So there is absolutely no difference in radius of convergence. And then this guy, if I evaluate, like if I try to take limit as z tends to alpha, so since this is a power series holomorphic function, so it's same as evaluating this power series at z minus alpha. So this is going to give you only a minus 1. Is this clear? Yeah, this is a
Yes, sir.
minus 1 as summation. I can write n bigger than or equal to, let's say, minus 1 a n z minus alpha power n plus 1 has same radius of convergence. Same radius of convergence as summation n bigger than or equal to 0 a n z minus alpha power n. Okay, so there is no change actually. So therefore, it's holomorphic and the limit is a minus 1. So the first formula which I gave you, that one is very simple to derive. If it is a simple pole, I can immediately do this and get hold of my a minus 1. Okay, so the other formula that I have given over here, that one in some cases that becomes useful as well. So like especially when your functions are in the form of a rational fraction, in those cases this becomes quite useful. So let us do that. Um let's calculate this one. So what do I have? We have f of z is equal to az by bz. Okay, so this equality is on again b alpha r minus alpha. Now what is, I already know that the residue is z minus alpha into f of z. So residue f at alpha is limit z tends to alpha z minus alpha into f of z. Now I can replace f by az by bz. Will you agree to that?
Yes, sir.
Because it's valid. This is equal to for the deleted in the deleted neighborhood. So this is limit z tends to alpha. I can write this as, let us keep az as it is. I know that b vanishes at alpha. If you remember correctly, b vanishes at alpha, but it's a simple pole. That is what it was given, simple 0. So that means b alpha was 0, but b prime alpha is not equal to 0. Very nice. So I write this as bz by z minus alpha. Now I can write this as limit z tends to alpha az divided by bz minus b alpha divided by z minus alpha. Okay, this is what I how I wrote. Now tell me, what is, if I take z tends to alpha, what is the limit of the numerator?
Alpha.
A alpha. If I take z tends to alpha, what is going to be the limit of the denominator
B prime alpha.
b prime alpha, and I can put together over here because I know b prime alpha is not equal to
Non-zero.
exactly. So do not blindly divide by a limit, okay, unless you are sure that the limit is non-zero. Here, of course, we know that b prime alpha is not equal to 0, so I get that the limit is a alpha divided by b prime alpha. Okay, so often you don't have to calculate all this LoRa expansion and all that. The moment you see that you have your function is given by ratio of two things, and the denominator has only a simple pole, you can just blindly take derivative of that guy and evaluate at alpha. You can take the numerator as it is and evaluate at alpha. So that's going to give you the residue. Very nice. Okay, so now this is about the simple pole. What can I do if I have, let's say, a pole of higher order? Okay, so let's take only that case, and today we will perhaps finish there. Okay, so the case 3 is pole of higher order. So I am going to next address the case of pole having higher order. So let's say pole of order m and n is bigger than 1. Now the point is, you see, when I have a pole of higher order, then I can write, so again you can think of writing the LoRa expansion. So I can write, let's say, a minus m z minus alpha power m plus a minus m plus 1 z minus alpha power m minus 1, and so on and so forth, a minus 1 z minus alpha plus a0 plus a1 z minus alpha, and so on and so forth. Now the problem here is that I cannot no longer mimic the previous process, because if I try to multiply by z minus alpha power m, I can do that, of course, but then this guy, when I evaluate at alpha, all I am going to get only this term, correct? Isn't it? If I try to multiply by z minus alpha power m and take limit as z tends to alpha, or try to evaluate at alpha, all I am going to get is a minus m, right?
Yes.
Yes. So therefore, it's not going to come as simply as in the first case, or as in the case of simple pole, but we still have scope of doing things, because you see, the moment I multiply out z minus alpha power m in the numerator, then what I get, that becomes a power series, and once it becomes a power series, you nevertheless know how to recover any coefficient for that matter. It's not only matter of this one is evaluated at alpha, but you also know what is the next coefficient. Next coefficient would be, you take derivative and then evaluate at alpha, correct? Because when you take derivative, the constant term will go away, the next degree, the first degree term will become the constant term, and then if you evaluate at alpha, you are going to get the next term, correct? And similarly, if you need like, let's say, a minus m plus 2, you are going to differentiate twice, and then 2 times you are going to differentiate, and then you will get evaluate at alpha. Okay, so therefore in this case we will not do things blindly. Of course, when we differentiate, you are going to get like, while taking derivative, you will gain some more coefficients like factorials. So we just need to be slightly careful. So let me just tell you what is going to be the formula in this case. Okay, so I have told you the idea. Okay, it's not going to be just evaluating, but it's going to be evaluating after taking derivative. Okay, so if we have, of course, this formula will be true for m equal to 1 also. You will see, if we have pole of so if we have a pole at alpha of order m, then residue of f at alpha is going to be 1 by m minus 1 factorial limit z tends to alpha, m times derivative, let me write of this function gm minus 1 times z, where gz is equal to z minus alpha power m times f of z on b alpha r minus alpha. Okay, so you take that particular function z minus alpha power m times f of z on b alpha r, so it's going to be given by a power series. Okay, I just don't want to write on b alpha r because on b alpha r this does not make sense. So on this deleted neighborhood you have this function g, which you obtain by clearing the denominator, and then you differentiate that function or that particular power series m minus 1 many times and evaluate at z equal to alpha, thereby you get the residue at alpha. Okay, so this is precisely what is the content of this finding residue at alpha. Okay, so clearly you can see that, for example, if I have a pole of order, let me write m bigger than or equal to 1. Okay, so if I clearly, for example, if your pole is a simple pole, so then you don't have to take any derivative. Means you are supposed to take m minus 1 times derivative, but if your pole of order 1, then m is equal to 1, so you don't have to really take any derivative, because your gz is just going to be z minus alpha times f of z. Okay, so that recovers the previous formula. So I'm not going into proof of this in detail. Okay, so you just I have already explained, right, that you write, so, or let me just do that, write f of z equal to a minus m z minus alpha power m plus so on and so forth a minus 1 z minus alpha plus summation n bigger than or equal to 0 a n z minus alpha power n, then in a deleted neighborhood what I get, g of z is a minus m plus a minus m plus 1 z minus alpha plus so on and so forth a minus 1 z minus alpha power m minus 1 plus summation n bigger than or equal to 0 a n z minus alpha power n plus m. Okay, so this is what we get. So if you take the m minus 1th derivative of this power series, okay, so if I take means like this is not, so let me just set this one. So set gz equal to this, then the m minus 1th derivative of g is going to be just m minus 1 factorial a minus 1 plus summation n bigger than or equal to 0 n plus m so on and so forth up to n plus 2, and then uh, z minus alpha power n plus 1. Okay, so this is precisely what you are going to get, and hence so limit z tends to alpha gm minus 1 z is m minus 1 factorial a minus 1. Okay, and therefore this is equal to m minus 1 factorial residue f at alpha. Okay, so the residue is 1 upon m minus 1 factorial limit z tends to alpha z to g to the power m minus 1 z. This is precisely the formula I have explained. Okay, now the point is, this two the first case was about removable singularity, the subsequent cases were about polar singularity. You can ask me that what can we say about essential singularity. So in case of essential singularity we don't have any luck. Okay, no ways, no way other than looking at the LoRa expansion. Okay, so you really need to have the LoRa expansion to know what's the residue. I cannot say anything because primarily, as you can see, the LoRa expansion is not terminating, right? So I cannot get hold of any holomorphic function out of that essential singularity. Like if a function is having an essential singularity, I cannot think of any polynomial which I will multiply and make my function holomorphic. I cannot do that. Okay, so that's the reason we are stuck over here. Okay, really, like, for if you just imagine e power 1 over z, to make e power 1 over z holomorphic, you really need to multiply by what? Like you cannot multiply by some polynomial and make it this thing, right? So that's going to be difficult. So therefore, for essential singularity, we don't have any luck, okay, regarding these things. So fine, I'll stop over here, and in the next class we will define something called winding number, and after that I will state what is Cauchy-Decision theorem. Okay, so that will be the content of next class, which we will do on Monday, and then we will see some examples, applications of Cauchy-Decision theorem, and other stuff. Okay, so are there any questions?
So what about the quiz?
Yeah, so